Hello all, welcome back. Today I am really excited to talk about the Muon g-2 experiment because the experimental results show strong evidence that our best theoretical model of the subatomic world is incomplete. Muon g-2 is a particle physics experiment at Fermilab to measure the anomalous magnetic dipole moment of a muon, which will be a sensitive test of the standard model of particle physics. The strong evidence that muon deviates from the standard model calculation might hint at exciting new physics. Muons act as a window into the subatomic world that could be interacting with yet undiscovered particles or forces. Next, let me talk about a muon. What is a muon? The muon is an elementary particle similar to the electron, with an electric charge of -1 e and a spin of half, but with a much greater mass. Its mass is 207 times the mass of an electron. It is classified as a lepton. In particle physics, a lepton is an elementary particle of half integer spin that does not undergo strong interactions. Let me talk about the standard model. The theories and discoveries of thousands of physicists since the 1930s have resulted in a remarkable insight into the fundamental structure of matter. Everything in the universe is found to be made from a few basic building blocks called fundamental particles, governed by four fundamental forces. Developed in the early 1970s, it has successfully explained almost all experimental results and precisely predicted a wide variety of phenomena. Over the time and through many experiments, the standard model has become established as a well-tested physics theory. I'm going to discuss about the spin and angular momentum of the elementary particles. Spin is an intrinsic form of angular momentum carried by elementary particles. Spin is one of two types of angular momentum in quantum mechanics, the other being orbital angular momentum. The spin angular momentum of electrons is quantized and it can have values +½ and -½ The experimental proof for the spin of an electron is Stern-Gerlach experiment in 1922. We talk about some fundamental principles in electrodynamics. When a charged particle is at rest, there is only electric field. When a charged particle is in motion, there is both electric and magnetic field. From classical electrodynamics, a rotating electrically charged body creates magnetic dipole with magnetic poles of equal magnitude but opposite polarity. The analogy does hold good since an electron indeed behaves like a tiny ball magnet. Equation for magnetic moments in classical physics: mu is equal to QL by 2m, where Q is the charge, m is the mass, and L is the angular momentum. Equation for the magnetic moment of electron: mu is equal to G into Q by 2m into S. Here, S is the spin angular momentum, m is the mass of electron, and Q is the charge of electron, and G is the G factor. We are more interested in the G factor. Fermilab's g-2 experiment is used to measure this G factor. What is this G factor? The classical result for magnetic dipole moment is corrected by multiplying it with a dimensionless correction factor G, known as G factor. A G factor is a dimensionless quantity that characterizes the magnetic moment and angular momentum of an atom, a particle, or the nucleus. The parameter known as G factor indicates how strong the magnet is and the rate of its gyration. The ideal value for G factor is 2. Now let us discuss in detail about Fermilab's Muon g-2 experiment. Muon g-2 is a particle physics experiment at Fermilab to measure the anomalous magnetic dipole moment of a muon, which will be a sensitive test of the standard model of particle physics. The experimental setup consists of a 50-foot, that is 15-meter diameter superconducting magnet with an exceptionally uniform magnetic field. The Muon g-2 experiment involves taking muons and put them inside the big magnet, where we store them and send them around. The magnetic moment measurement is realized by 24 electromagnetic calorimeter detectors, which are distributed uniformly on the inside of the storage ring. The experiment has an extremely high level of precision. The chance that the results are a statistical fluctuation is about 1 in 40,000. The new results does not agree with the standard model prediction. See, this is the theoretical value and the experimental value obtained after Fermilab's g-2 experiment. You can see there is a huge difference in the theoretical value and in the experimental value when we consider the atomic scale. The strong evidence that muons deviate from the standard model calculation might hint at exciting new physics. Muons act as a window into the subatomic world and could be interacting with yet discovered particles or forces. Now let me talk about why this name g-2 experiment. See, the anomalous magnetic dipole moment is equal to the experimental value of G factor minus 2. Minus 2 is the ideal value of G factor. That's why g-2 experiment. That's all about Fermilab's g-2 experiment. Thanks for watching. Please like, share and subscribe.